All right, guys. So remember a few minutes ago when I was saying how much I saved my own badge with the API trace replay stuff. One thing to say is there's a bit of a development task involved in making a binary API and making them properly traceable and properly scripted. What I want to show you first of all is kind of the end result of the exercise, which is just how to drive the API tracing and replay stuff. You'll notice if we go look at, and you all should have this, etc. Yes. This guy, you'll notice the magic save barracks life API trace on. This is in the start, the command line orgs. You almost always want to be tracing API messages. The circular buffer is set to something like 128K worth of entries. Sometimes, yep. At any rate, so the idea is if you turn the API trace on, we can rapidly work out what the default size is. I typically, I always start the thing this way so that if you're doing control plane API tracing, you guys have played with VPP Kittle? Well, VPP Kittle turns out to be a wrapper for which is the API trace test tool. And eventually, there we go. Now notice one piece of amusement is the API test tool also does plugins. And when building a function in a plugin, you can also build a plugin for this guy so that the API trace tool knows how to, for example, send the binary API that's implemented in the data plane. There's a little bit of complexity around about numbering spaces, because you can imagine a lot of the message API numbering is done with constants, and what we do is is a fairly simple allocator scheme to just give each plugin its own numbering space, and the numbering space can change, but the code involved actually won't. The way we threw it together. So let's try the simplest thing. The API test tool directly has an exec command which says send debug CLI commands to the data plane. If we do a show interface command, you'll see, oh, whoops, I know what I need to do. I need to restart it, so it's not doing so well. All right, so there we go. And now if we go back here to Mr. API test, you'll see that there's gigabit Ethernet 080, and it's actually down. Now, the API test tool is perfectly happy to send script like so. And each one of these is an ASCII encoding of one of the binary API messages. I mean, the two obvious ones here are set the interface address and set the interface admin up. And if we go actually pick this stuff up and splat it down in the API test tool like so, it'll send those two messages, and then we can, whoop, what did I do this time? All right, I confused myself, so let's do, and now you'll notice that son of a gun, the interface is up, and oh, by the way, there's its there's its interface address. So another thing we can do is just to tell the data plane to please save an API trace. So exec, meaning send it to the data plane as a command. Okay, notice again I went through some long dog and pony show about mapping the names to a place that's safe to actually write files. You can then actually ask the data plane API trace. And this is what it looks like. We might as well start at the beginning because there's some interesting stuff. This mem client create API message. If you go look into the API definitions, which we ought to do at some point reasonably soon, the first thing that any client will do when it hooks up is send one of these memory client create messages. Notice it says who it is. then VPP API test, the container shell is going to send several binary API messages of the form, hey, please dump me the following kinds of interfaces. So what the test tool is doing is it's effectively building up an interface table so that when you talk about interfaces, it's just learned from the data plane what there is to know about the kinds of interfaces you might want to know about. Now, this, I said a moment ago, multiple plugins, Mumble numbering space allocator. Well, it turns out that that get first message IDT message is a tool that a plugin can use to, a control plane plugin can use to go discover its friend, the data plane. This is actually a kind of a cute little scheme that the APIs turn out to have signatures, and what the control plane client does is to say, hey, look, I know there's supposed to be a data plane plugin loaded with the following API name concatenate signature, go look it up. Now, one thing, obviously, this isn't the prettiest pretty printer, so we might want to go fix that in a minute. It's certainly, if we don't actually do it here, we can whack it together in 5 minutes in the Hackfest. It's very easy to add custom dumpers that do this, script colon and here's something to do. Now, if we look a little further down here, we'll see, here are the two interesting guys in the script, which are to say, I want to set the software interface add del address. Software IF index 5 turns out to be the captured and then pretty printed version of gigabit Ethernet Mumble. If you look at the interface table, 5 is going to be that gigabit Ethernet interface. Reason we do this is that there's actually a second order subtle thing that I do with this mechanism fairly commonly. Remember I've said, you take an API trace, you can capture it, you can turn it into a script, and then you can replay it. I'll show you the replay in a second. One of the nice things you can do is by a little bit of connivance to replay a trace on a completely different instance of the forwarder. In fact, one that doesn't even have the same interfaces. It's because the software IF indices are allocated in just straight up, end of the vector, make me another interface kind of order. You can really easily imagine creating some loopback interfaces so that you can replay a control plane trace taken from some big old router that has 20 real interfaces, and you can secretly say, well, this will replay fine if I just cheat and make a bunch of loopback interfaces. And it turns out when you're looking for a bug of the form I was describing earlier, where you have some guy in a test lab, churning routes up and down for a day. He's made 300,000 of these transactions. The chances that you're going to really want to even A, use his box so that you have exactly the interface configuration, or B, even talk to the guy much. I mean, the standard speech I get is, oh, the data plane's not passing traffic. Fine, where's the binary API trace? Oh, okay, I'll go figure out what the problem is. I cuss 3 times and then I go, I go dump the API trace and look around, or I'll replay the entire API trace and look at the tables. That those are the tricks of the trade for debugging stuff that happens as a result of control plane actions. I mean, the other thing is, I should probably show you this handy place, which is in BPP. Let's just look here. This guy, OS panic is the court of last resort right before causing a core dump. And you'll notice this message API postmortem dump guy. The idea is if you miscode a message handler badly enough, or if something in the data plane just gets indigestion and gets a bus error or something or other, including the last message that was possibly in process of being executed, you get the entire trace. So if there's some static, I send one of these messages with the parameters in it set a particular way, you actually will get an API, a postmortem dump of it. The binary API traces tend not to be very large. They're especially not large, when compared with a core file. And folks, when you want to go, submit a gyra against the data plane, in future when folks are doing a lot more with control plane transactions. It's really good to say, oh yeah, by the way, and here's here's where I drop the Postmortem API dump. What the things these will do is they'll show up in a file called basically temp API postmortem.pid. In fact, why am I talking about it? Let's just do it. All right, let's see. Oh, this is a production image, so it doesn't have the handy crash command. Oops, sorry. At any rate, so we're not going to be doing that little exercise, but offline you can verify that if you play a certain number of API messages into the data plane and go cause the thing to shoot itself in the foot, just do an obvious bogus pointer reference, you'll see that you get an API postmortem trace. And again, it's not so, with your data plane blinders on, it's not so important. But the mechanism is really, it's a lifesaver. It's the only reason I still have my company badge, because a couple of 3 years ago, I would have definitely not been able to debug the sorts of issues the guys were running into. So that's kind of the pretty print portion of the exercise. The next thing to say is, okay, if we look at the interface complement, okay, this guy's all configured. So let's actually restart VPP once again. And then right, it'll take itself a while. And that's the just go replay the trace. It's really snappy, especially compared with the typical control plane. And then now if we go look at the interface complement, you'll see that, yes, indeed, it's replayed the trace, the interface is up, yada, yada, yada. So, in fact, the really cool thing, that you can do is to take an API trace, pretty print it, turn it into a script, and then use the script as a method of saying, okay, here's 100,000 transactions that the data plane, that the control plane is willing to do. By the way, I know kind of what the tables are supposed to look like at the end of that exercise, and kind of use it as a regression test to make sure, first of all, the trace actually replays, and second of all, that you get the tables right. That this is something I haven't done a huge amount of. I mostly use it as a debugging tool, but at any rate, the facility's in there. It's a little bit more targetable than that. Let's just bag out of here and. Now, if we were to, all right, let's do the the more raw form dump. API test, and if we were to say not custom dump but Plano dump. Whoops. You'll see here's just a generic print of all of the guys, and notice that they have some pretty nice sequence numbers. If we look here, you're going to see that. Let's see. Okay, 9 turns out to be the guy that adds the interface address, and if you want to, you can say the API trace. First, okay. Now notice in this case we replayed one of the two interesting messages, just the go install the IP4 address, but not the software interface set flags message. The point here is that say you have a long trace and somewhere in it something goes wrong. Well, binary search is your friend. You can take a trace of 100,000 elements and just start cutting it in half until you find stuff. I've resorted to that at times too. So the replay mechanism has a little bit of steering like that. Which is to say you can replay, 1 or n messages. I mean, if you tell it to do something utterly silly, it'll probably give you a little bit of advice about it. So we know for a fact there are not 9 million guys or 9,000 guys in the trace, and it'll say, okay, mumble, a little bit of El Stupido checking because I frequently do typos. So there's the trace, replay, sort of binary dump and custom dump, sketch. The commands are, I believe, reasonably well listed on the wiki. If they're not, somebody needs to yell at me about it, and we'll get it done, because this stuff is not immediately important for building a new feature, but it's real important when you start doing control plane integration. Folks have questions about this before I go on to yapping about something else? Keith, man.
You've actually got a YouTube of this as well.
Yeah.
On the wiki.
Yeah, it's probably not greatly different than the dog and pony show I did here, but at any rate, yeah, I do. Others?
Even if you are building a feature, right, I think unity testing that is very useful, and so this is really valuable.
Yeah. Well, and like I say, it's the only reason I still have my badge, because I would have surely been fired for gross negligence to not be able to do this. The replaying and cheating to make loopback interfaces is a sort of a second order subtle trick that didn't take too long to think of. The other thing is this API mechanism has been around, God, I'm going to say almost a decade. So it's pretty much a source of truth. Have folks looked yet at the binary API definitions at all? Have we shown guys that? Okay. Do we want to go there, or what would folks like to do? Because I'm more than glad to show you. It's like, okay, I've been saying here's the here's the software interface up-down message. Let's actually go look at it a bit. API. Okay, this is the actual API definition. SW interface add. Yeah. What ends up happening is this is it's what do you want to call it? A little RPC generator. What comes out of here are fundamentally C type defs, some definition, some boilerplate definitions of the sort of the generic dump this message in binary kind of thing. All of these messages are, some details. All the messages are in network byte order. So when you see a 32-bit quantity software IF index, because it's supposed to be sent in network byte order, not in host byte order, we have at times interoperated between, interoperated using this message between control plane running on one one endian flavor and a data plane running on another. All of these messages can actually be passed via sockets. We don't ordinarily do that, but there is socket code in VLib-API that can eat these same kinds of messages and produce basically the same results. So you can imagine doing a stream socket. That code isn't heavily used, because most typically what you do is you put an agent right next to the data plane to shove stuff in its ear. The underlying mechanism is capable of at least a quarter million routes a second, probably far more than that, depending on the platform and so on. But these are binary messages passed in shared memory over unidirectional, lock-free queues generally. So. The underlying mechanism, and frankly the little bit of control plane that's in the data plane to go paint the fibs, to do things like setting interface addresses, is very fast. There's some interesting, here are the API definitions. If we look actually at what comes out of the build root VPP. All right, that's why I'm not finding it. This is the actual, compiler output, and there's some sort of boilerplate shite thrown out. Ooh, possibly want to go get rid of that stupid copyright, which is kind of wrong. Again, it's going to produce you fundamentally a macro with all of the with all the message names, and down at the bottom is actually a little detail, which is this guy. It turns out that in the compiler, the lexical analyzer is fairly smart about accumulating CRC32 of all of the non-white space octets and non-commit octets the thing runs over, so that the data plane and control plane really have to agree on the checksum, or they won't even connect. but it's possible to imagine. I mean, anybody who's worked with this sort of system, you say, here are my APIs. Here's a nice version that's invariant if you go add a couple of comments or bump in a blank line. But if you actually change anything, the signature is going to change. In plugin world, you remember I was yapping about. Let's see, build root. Let's go look at sample plugin, which is the MaxSwap plugin, more or less as is. Sample, and then we say sample.c. This would be MaxSwap.c pretty much verbatim. I'm just looking at. See this? This is the control plane plugin to data plane plugin. API signature rendezvous. In other words, I'm going to make up a string in the control plane plugin that says, oh, I really ought to be finding something called sample, or in your trees it would be called MaxSwap. And oh, by the way, here's the version so that you can you can do that same level of rendezvous from an API test tool plugin to the data plane plugin. The other thing it ends up wanting to do is this, get message IDs guy. That if you think of 20 plugins thrown in that directory and all of them enumerated, in order for them to get their numbering spaces straight, somebody's got to restore order. And what this message ID base guy is literally the first message ID that you're supposed to send this time. So straightforward stuff, but. You do definitely want to do it. Let's see. Is there anything more to yap about that? Well, let's actually maybe see if we can go find this puppy here. Oh, no C-scope. I'm a monkey. Okay. Well, at any rate, where would that be? That would probably be in. Yeah. Maybe I don't want to go there. At any rate, if you guys tag search for that one. Hey Keith, can you work out maybe where that routine is for me?
BL message API, get message ID.
Yeah, that one.
Yeah, that's in VLib API, VLib API, API shared.c.
Yeah, thanks. Yeah, sorry, I just don't have the tags built.
You have to yell it out though, because I can't see the text orthogonally, so just
Yeah.
yell what you need.
All right. Oh, all right. I'm going to just try. Okay. Right. Yeah, mumble. Message range by name. This guy gets bootstrapped, and it says if I already, yeah. This guy is an implicit registration of the control plane client, and if for some reason, the standard reason being, you change the name of something, subtly, you didn't clean out the plugin directory. Now you've got, multiple guys trying to register for, register as clients for the same API. It'll at least announce it to you. But there are ways of hurting you with this stuff. But if a plugin asks for a ridiculous number of message APIs, it won't do it. Otherwise, it'll it'll reply. Now, let's look at the message handlers just a little tiny bit, which is to say VPP. And this, the API messaging has been historically segregated away from the network stack, that it's viewed as an application on top of the basic network stack. And as a result, the API message handlers and definitions lives in the VPP component. You can imagine making, particularly out of VLib, something that's doing vector processing that might have a binary programming API, but it's totally different than the one you'd want to use with the network stack, because you might not even be loading the network stack. So as a result,
can I ask a question?
Yep.
Sorry, just before you move off, you're talking about control planes sending messages down. I know you haven't necessarily been that heavily involved in Honeycomb, which is another project.
Yep.
Yeah. So, but as far as VPP is concerned, Honeycomb's just a thing consuming the JNI version of this, correct?
Yeah.
So,
oh yeah, the other thing to say is that API compiler is also willing to spit out JNI bindings, Java bindings. It would be easy, I've heard rumors of someone having slapped together a Python binding, and it'd be, again, easy to go make the API compiler spit that stuff out. In terms of what can you automatically generate versus what do you have to manually do, The initial connection stuff probably has to be hand coded once, but an API that says, here are a bunch of parameters, give me a 0 for good, give me a negative return for bad. That stuff is easily auto-generated. In fact, if you look carefully as you're building VPP, you'll see the component called VPP-JAPI, JAPI, which is the Java API, and you'll notice that it ends up compiling a mix of some hand-rolled Java code and a bunch that's done by the API compiler. In fact, one of the things you can look at is if we go look at this guy, substantially, yeah, I mean, here you see one where the software interface dump function ends up needing to have manual Java code, but anything that doesn't say manual Java is going to get auto-generated Java code. The API compiler is, it's a little bit of a historical artifact in that it's a full-bore, YAC compiler that I built starting, God, must have been 1996, literally, for various other projects. And what it ends up doing is to produce, again, C-typed Fs, yada, yada, but it also produces Java code. And teaching it to do Python would take, a few hours to remind myself how the bloody thing works, followed by somebody has to teach me Python because, again, I'm a caveman. I know from YAC, but not so much from Python.
That comment says works. Does that imply that the other ones don't works?
No, that comment implies it should have been. How would you put it? When I was first manually generating this set of APIs about 4 years ago, I would mark them when they worked, and apparently that comment never had an accident. No, obviously the software interface add-del address doesn't. We've tried to do some level of doxygen tagging in here. Yeah, it works. Yep. You could easily submit a patch set for that one. Yeah, I'm as I say, I'm hardly dictatorial, but yeah, something mumble. Okay, I'll stop clowning around. But yeah, at any rate, you get the general program. So what do message handlers themselves look like? If we look at API.c, here's the epic catalog of all of the binary API message handlers, and let's look for SW interface set flags. I should go through this a little bit because people are eventually going to want to define their own binary APIs. It's probably too bad we don't have a couple hours to go through this. You'll notice that the MaxSwap plugin actually does have its own binary API, the one that Keith was showing you to turn on and off the max swapping. But this is the fundamental for each VP API message. This is the epic catalog of messages that are understood. Things of the form want underscore are registration APIs for pub sub, push model things like interface events. The interface events one is real straightforward. Link up, link down. Thank you very much. And if you as a client, if you use a control plane client, need to know that, you want to use the VL API wander interface events T type from the sent from the client that'll hook you up, and then it'll start randomly announcing interface events. This netconf server stuff is historical junk, which again need to be rototilled. There's a reasonable long list of stuff. Let's see, interface set flags. Okay. Now notice that this handler is a little bit stylized. Many of the APIs take software IF indices as one of the parameters. Because quite commonly you're saying blah 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 to the interface. Well, to the interface means generally that you want to go validate the interface. Again, these macros are at the top of the file. They're pretty bloody straightforward. Do a little bit of brain police on flag mapping, and then go call software interface set flags, which will go make the go make it so, Mr. Data. Notice the ever popular endian swap. One way of confusing yourself is to forget this, and then you're going to call some underlying function with something that's generally a gigantically big number that you didn't intend, and see also assert time. Let's see. C-lib error report, I don't want to go too far into that, but the point is the software IF index validator expects there to be a magic label, and at that point in the game, what it'll do is to populate this RV or return value with some negative code that says something like bad software IF index. And the API test tool is pretty handy about this. Let me just show you an example of that guy getting a little annoyed. So if we were to say software interface set flags X11 admin up, it's going to tell you, thank you very much. We don't have a such an interface. In fact, exec show int. You notice that the interfaces we have are 0. 0 is the local interface always. 1 through 4 is always the package. The 4 pre-allocated package generator streams. Software IF index 5 is essentially always the first interface discovered in PCI probe order, Filament 11. You can almost always, if you want to use, to pick a software IF index that's valid, you can almost always pick 5. 11 in this case, the guy's AMP really doesn't go to 11, so you get out of the binary API, you just get an immediate, thanks for playing honk, invalid software IF index. The header file, which has the canonical list of thanks for playing codes, is actually vnet API erno, and you'll see that there's quite a collection of annoyances. Invalid software IF index is -2, blah blah blah. Feel free to add your favorites. We're not going to run out of them anytime soon because they're generally 32-bit integers worth. I've seen schemes that do all sorts of crazy error encoding, but ordinarily what they are is just a lot of typing and not very much value add. That really, just a simple set of incrementing numbers. I'm too much of a knucklehead to do anything better. And oh, by the way, it's very easy to build a table that says -66 is this one, -67, because it makes you a nice dense vector, rather than having bits splattered all over the place to say, well, it's this component and this subcomponent and this Dewey Decimal System, whatever the heck. Between any two real numbers, or exist two numbers, one rational and one irrational, yada yada. Not necessarily the be all and end all of usability. There's no problem at all with adding more within reason. So, on this general topic, this brings me back to a point that we started to make with Keith, which is. Let's see, even in the Mac swapper, let's do sample.c, even in here, under CLI, okay, so here's the sample command, and you remember this coding pattern that I was yapping about from the corner, where you say, make yourself a debug CLI command that does a bunch of input parsing, gets together some variables, and then calls an underlying action function to make something happen. Well, if we look here in the control plane component, if we look here in the test.c, you'll see. Actually, what I really want is the handler. X grep. Let's look for the handler. Right, okay, so that would probably be this guy. If you look at this guy, you'll see he does exactly the canonical thing I've said, where this is the binary API message handler defined by the sample plugin, and he's going to go call that same underlying action function that the debug CLI does. This coding pattern is, we arrived at it. It really makes life better because you only have to debug the actual guts of it once. All of the tunnel setup, all of the tunnel setup stuff, and some of those take quite a considerable number of arguments to the point where rather than passing individual arguments, I pass an args-t so that when I have to add the I plus first argument, I don't have to go run around and type in 20 places to do it. The idea is have an underlying action function that actually makes something happen. Call it first from the debug CLI, then when it comes time to build the API message handler, it'll look relatively like that. Notice that, notice this sample max swap enable disable guy, which we hope is adequately suspicious. Right, let's see if, all right. Notice that this guy actually is doing the right thing, which is to check. And this is a more manual, this is a more manual version of that macro you saw in the API test tool, but it's the same basic game. You say, did this guy just hand me, a fish, film at 11? It's literally this, this utterly wrong guy that was returning that error code that got reflected by the API test tool. That's literally, how and why you got the invalid software IF index diagnostic. Is this making sense to guys? I hope I'm not belaboring the bleeding obvious. So Keith, where do we go from here, man?
I was next cab off the rank was the classifier.
Oh, now we get to really confuse everybody. Oh, good, I love this. So fine, classifier.
These are not the vectors you see.
Yeah, well, yes. Well, actually, Keith brings to mind a good point. The classifier is a kind of a different cut on doing ACL or very general classification than you might see in a typical code. I've seen n-tuple classifiers that work by fishing particular fields out of packets and pasting them in a structure and then going and looking up to see does that match anything and searching through a list of possibilities. The one bug with that is by the time you start fishing around in packet data, you've kind of burned an awful lot of clock cycles you didn't really need to. The take I had on the problem was to do rather a different thing, to say, look, the MMX unit, the AVX units on x86-64, even the vector unit on PowerPC or the vector unit on the ARM chips, is really good at just rumbling along. And imagine a world where you weren't so concerned about having some you weren't so concerned about fishing stuff out to make up just exactly the structure you wanted, but you say, look, if I tell the control plane, hi, I'm a dumb robot, you hand me a bit mask starting at about where the packet DMA began, and you rumble along using the vector unit as kind of a big wide load story unit, doing doing data, packet data and mask, accumulating a sum, then doing a hash. All of a sudden, you have a really fairly fast classifier that doesn't have very much of an opinion about what it's classifying. And that's ultimately, from 100,000 feet, exactly what the VNet classifier is like. Let's go look at VNet.
So but semantically what it means. For example, the tuple, right? You are able
Sorry,
to
can
say.
you just put your hand up so you can get a mic?
Yep.
So when you take the phi tuple, you are able to say, when you take the phi tuple, you are able to say this is the source, this is the destination, this is the property of this flow. So you are pretty much coloring the flow, right? And then you are doing action.
Yeah,
Now,
yeah.
When you do this, what is the semantic? Because
Okay,
you're saying,
I'm going to show you exactly how the classifier itself in VBP at the moment is a really dumb robot. What it let me show you the look, what it actually does.
thank you.
Okay. Now the table programming involved in this is really the hard part of it, but the actual rumble along is not. I'm using a bounded index extensible hash. What I actually do to, you notice there's a little bit of conditionalization around it, but the idea is you say, how many vectors am I supposed to match? I mean, it'll match up to 5 by 16 octets at the moment. Yep.
Can you please repeat the name of the hash that you were using?
Okay, Yep. Well, we're about to get there. Let's see. Yeah, it's actually, if you go look in VPP-infra xxhash.h, it's Google xxhash, and what I'm doing here is I use the vector unit to do a bunch of XOR summing of yeah, how would you put it? You start off saying if you're not matching at least one vector, why are you doing this? Let's look at the SSE version of it, where you say data in this case is expected and generally turns out to be the DMA target, as in data sub 0 in the VLib buffer T. What you do is you say, okay, depending on what you're matching, you might want to skip several times 16 octets and then actually start matching. So the classifier table skip n vectors tells you, okay, skip some number of vectors. Now, it turns out if what you want is just to classify on the IP4 source address, you get to skip the first 16 octets because the IP4 source address doesn't span that boundary. It actually lands in the second 16 octets. Notice, yeah, Keith?
Can I maybe help with a picture from the other day?
Oh,
Would that be useful?
It probably.
Why shark?
Okay, yeah, could
Just super
do.
quick so people get context, and I'll flick it back to you.
Yeah,
just
well,
to help.
yeah. Again, this is just, this is
Pretty standard
right.
stuff.
Yeah.
Just sorry, just super quick.
Yeah. Tag team is good.
Yep. Usually good. Okay. So, top line of Wireshark, 16 octets. DC IP protocol or the IP header, our type 40.
4500.
Yeah, exactly.
And then actually the length is 0054 there.
Oh, yeah.
Now,
Exactly.
yep. Now, yeah, as you see in the second 16 octets right here, oh, I know what I need. I need my magic Lauren Cooney tool. Yeah, I need the Lauren Cooney tool. All right. I've got the piece of cat magic. Yeah, that again, as Keith is saying, right there is the source address. So within the second vector, starting at DMA start, you'll find the source address. At least with this L2 and cap. Now, one of the complexities involved is that you might imagine a case where it's like, okay, sometimes stuff shows up on untagged. This is an untagged packet. 1 or 2 VLAN tags will shift stuff around a little bit, and you end up with this classifier as is currently constructed. If you start from the DMA start rather than from a networking layer boundary, you end up getting to make sure that the masks match the L2 type a little bit.
I'll get out of your way.
Oh, no, not a problem.
Thought it
No,
might
no.
have been helpful.
No, appreciate it. Thanks, man. So, drum roll, please. And there we go. Drum roll, projector. Going once. There we go. Okay. At any rate, so what you do is you program up the classifier table, mask, and skip so that you're rumbling across the correct piece. To do just a source classification, what this guy is going to do is it's going to compute literally, that second 16 octets ANDed with a mask that'll just give you the source address dropped in a particular place. The point there is the classifier's next move is going to be to match that against a set of sessions hanging off that table. The tables are actually changed, so if you're doing multiple kinds of, first I try this, then I try that, then I try the third thing, kind of, rules in order, the tables will end up, you'll miss at one level, try the next. The final table has a fallback, court of last resort action, which might amount to drop the packet on the floor. So this is the basic matching scheme. Now, one of the things that one of the exact places the PDK guys could really help out is this cannot possibly be the best the best way of even using the MMX unit. Moreover, AVX2 clearly you want to do, wider is better and faster. We're really kind of using this thing as a load store XOR, as a load store unit, some ANDing and some masking. That even though I'm ostensibly using, U32 or 4-byte integer by 4 vectors, what I'm really doing is just mashing bits together here. So
there's LibACL and DBDK. Sorry, I'll wait.
I'll go for it. Yep, wait.
LibACL in DBDK actually does similar things. I don't know that it's a direct replacement for the classifier you've got, because
No.
I haven't been able to even start to look at this.
Yeah, no,
But
again,
it
this
does
is,
use AVX2. It'll use AVX, or
Yeah.
actually SSE, and it's got a scalar version as well in case
Yeah.
you end up there.
I'm not necessarily, the integration piece is the lookup and matching is actually the part that you'd want to attack. This stuff isn't chopped liver. You can get one core, depending on the table size, you can get maybe 7-8 million packets a second through it. The place where there's some, where the concept that's actually a little bit important is, okay, now I've matched something, or I've fallen back to a default entry. Now what do I do? That's the piece that's actually quite neatly integrated with the rest of VPP. The actual matcher, would really be a place where contributions, thoughtful contributions that don't core dump, et cetera, would be appreciated, because I can't at all claim to have gotten the matcher to be anything more than correct. This is about the second time I've coded this. It probably needs a third round. Florine, what's up, man?
Just a quick question. Could we in the future have a table that does longest prefix matching as well here, or does it make sense, or it doesn't make sense?
Well, fairly standard IP4 or IP6 LPM?
Yeah.
Yeah, those guys, normally you wouldn't actually do that. You just simply go put the entries, in a VRF table, and then cause them to be walked in the normal manner.
Right. But if we want to do, if we want to avoid that, so if we wanted to go to the classifier first instead of going to the FIB.
Building a node to sort just earlier
Exactly.
in there. Yeah, that's certainly easily done. I mean, you could probably even use the IP4 and IP6, lookup inlines, and just make another node plummet into the graph slightly differently. And then based on, okay, I've taken a hit, look up next index sends the packets wherever you've decided you want them to go in the graph. Yeah, there's no trouble doing that. It just, plumbing work. Roll up the sleeves, get out your PVC pipe dope, and off you go.
All right, got it. Thanks.
At any rate, so the next thing to say is let's actually go look at a real use of the classifier, which VNet. Okay, this is an actual honest-to-God graph node which does IP classification, which is to say, it's going to look something like a standard graph node. Then what you end up doing is to say, this is actually an odd kind of graph node, which is to say, what you end up doing is classify inline. It's instantiated a couple of times. You can see there's a little bit of based on a constant parameter to an inline. It's saying, well, am I doing IP4 or am I doing IP6? Thank you very much. Now, this node is not completely dead stock standard in that it doesn't do the usual single dual loop paradigm. Problem with the classifier is it tends to run the world out of load store unit more quickly than other things. So although it does a pass to compute hashes based on whatever table you start on. Let's see. Here what's ended up happening is you've hit on an IP FIB adjacency that says, oh yeah, I'm a classify adjacency rather than a stock rewrite adjacency, and it'll go fish the details, figure out which of the classifier tables you're supposed to start on, and start doing some, bucket and also backing page, entry prefetching. The algorithm here, the hash and then lookup algorithm is actually a bounded index extensible hash. Are you guys familiar with that one at all? Does anybody know what I'm talking about? In 2 or 3 words, bounded index extensible hash is a rather cute finite number of memory probes lookup method where you have a bucket array of a certain size, you hash whatever it is, you read the hash bucket, and it's going to tell you a couple of things. How many quotation fingers backing pages exist for that guy? Always a power of 2. So you might have, this particular bucket has, entries that will fit in 1 backing page, 2 backing page, 4 backing pages. What you end up doing is you say, okay, well, I've got this hash code, and I just sniffed around in the bucket, and it said I've got actually 2 backing pages. Take one more bit of the hash code you computed and pick whether it's the top or the bottom, so that you then do one, you do 1 backing page probe. They're conveniently set to be, not very many cache lines. At which point you say, okay, I don't have to search the entire bucket. I just have to search in this, 1/2 to the nth of the bucket. So you really are doing, a fixed number of probes to get to the answer. Yep.
Yeah, I used that for IPv6.
Yeah. Yeah.
Used it mtry before.
Yeah. It's used in IP6 instead of an mtry walk. Simply because a 16-deep mtry walk is kind of a non-starter, and various we really ought to consider what to do with IP4, IP6 lookup anyway to see if we can use a better kind of tree bitmap lookup. But the v4 FIB is fast and thread safe, and the v6 FIB is not chop liver fast and is thread safe. You begin to not want to work too hard on the problem, given all of the other insurmountable opportunities one has to do development. So with this guy, we do a little bit of bucket prefetching, in a first pass, so in a first sort of dual looped pass. Then we say, go actually, there's a cleanup loop, and it's turned out that there are not enough load store unit slots available to dual loop the actual comparison, that it just turns out to work better if you go 1 packet at a time doing it. This is the sort of thing where, you tune and you tune and you tune and you finally say, oh, bleep, just, one guy's enough. It turns out that prefetching 3 ahead seems to work best for this code. The tuning of the amount of fine-grained parallelism you try and use, and the amount of prefetch stride you're using is a little bit of a black art. It's platform dependent, and in the spirit of wanting to be portable, extensible, and not terribly difficult to write, you ordinarily don't do that. You don't do a ton of tuning of this sort. In this case, it made enough of a difference I was willing to do it. But here, so what you do is you go find yourself a classified table, and now you do an entry prefetch 3 ahead. Usual speculation, blah 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 blah. Table index, and here now you finally use the hash and the table to go look yourself up a classifier entry, meaning a hit. If you get one, the thing you do is you say, okay, I use the L2 classify opaque, even though this might, I probably ought to instead of calling it L2 classify, I ought to call it classify. The opaque index is a magic number that the graph node you're about to send this packet to uses for its own convenience. Quite often it's classify mumble, here's the tunnel I want it to go out, here's something. It's a 64-bit opaque. And the next index is directly read out of the session, and off you go. Let's see. This is a little bit of a crazy person check to make sure you don't send packets to oblivion if the sessions are misprogrammed in some way. Any rate, so now what you've done is you've matched on some bits fished out of the packet. You said yes. Okay. Now, on the hit entry, what you've ended up doing is to say then, okay, where do I send this packet in the graph, and what little breadcrumb am I sending along with it for the next node that's catching it to process? That's the piece of it that's actually really quite useful, because again, you can then, in a subsequent graph node, you can refer to that data to go find the basic data structure, decide what you want to do with the packet, and off you go. So there's kind of a match and mask piece, a lookup piece, and then here's the opaque data that you paint into the buffer metadata. I'm going to go through buffer metadata in much more detail later, I believe. After lunch, when people are good and sleepy, presumably. The point is, the lookup engine. This is just a quick overview of how it goes, with probably enough file pointers that you can read through it at your leisure. There's a lot of debug CLI that goes with this to actually program the tables, which which let you say things like, oh, I want to match on, IP4 source dest, IP6 source dest, L2 things. And all it's really doing is computing a mask and a mask and match, mask and skip thing per table, and then a set of matches that are that have to be exact matched. Yep. So mic time. Thank you. Okay.
You mentioned the debug CLI. I'm having a little bit of trouble getting just arbitrarily classified packets to go to my node. Maybe we can do an example. That would be maybe useful for everybody.
It probably would be.
Basically, I don't know what I can do and what I can't do if I if I can say match on a UDP port number and then send it to my node, the node that I want.
Well,
and then what are the requirements in the node to consume
let's
those packets?
Let's go actually look at just the right place to talk about this.
And I've been following the mailing list where you had a example kind of command set that you were using, and that stuff's not really working that well for me.
Right. Okay. Well, what we might want to do is we might want to take it up offline. All right. I'm out. Yeah. Okay, this is the actual guy. Classify addDel session command. There are some stock places, in the graph today that have the idea of, you want classification at a particular point. L2's one, IP4, IP6 are others where you can install classify adjacencies. Making the matches, how would you put it? Have you tried ACL hit next and your favorite node and your favorite node name? Because that's how this works.
ACL hit next, then I've been using hit next. So I should use ACL hit next.
Well, yeah, you might want to try it.
Okay, to try all of the hit next.
Well, yeah, it depends if you want to. Yeah. Let's see. So you're basically.
Example, to send an arbitrary packet to a node, that would be useful.
Yeah, it's probable that I'm going to stumble around for 10 minutes up here, but let's take a note, and during the break, we'll cons one up for you, or better still, take your example and get it to effing work. How would that be? Mm-hmm. Yeah, I mean,
this is something you and I worked on a couple of weeks ago. You were helping me do exactly that. I had this imaginary graph node. I needed to do something, and I knew I needed to classify on some arbitrary part of the packet. And we worked on exactly this problem and found some interesting things that we want to do down the road. So I think there's a short answer, let's get it going. There's a longer answer about, look what we discovered while we did it, right? You had some good ideas about passing palms.
Well, yeah, I mean, one of the things used to be that we'd, we wouldn't even slightly help make it anything other than next index 5. And the code's been fixed up a little bit, really, thanks to Keith's input, or that large club he keeps under his desk to make me work harder. But yeah, no, I'll freely admit that the debug CLI is not really all that great amount of fun. The control plane APIs are real straightforward, but you're putting under the control plane the problem of, oh, dude, you have to be this tall to ride the roller coaster. You have to know which bits you want to match on and mask on. Otherwise, your mileage absolutely will vary. But let's go get your use case going, and then if you don't mind, Yeah, that's exactly what I was going to ask. I didn't manage to get there. Yep, question in the middle. Hey, Christian.
Yeah, so just to make sure that I got it right, so this classifier actually works, the way it works is like you have a topology, like a tree of tables, right? That you can jump, each entry in a previous table can jump to a different table going next.
It's really arbitrary what you do on match and what you do on miss. If you want to, if you want to do one flavor of classification and then do another, you can actually, pretty easily recirculate the packets. Again, directed graph, and oh, by the way, a node can actually re-enqueue to itself. So if you get into one of the classifier nodes and you want to, there's absolutely no rule against recirculating stuff directly. If what you're interested in is a linear, did it match this mask and set of matches? Did it match a different mask and a different set of matches? Just a linear scan, you don't end up needing to requeue the packets. It'll just do that.
Yeah, but typically the action that you execute is to go to a next table.
Yeah. Well, the action on hit is really to enqueue the packet forward in the graph somewhere.
Okay.
In other words, let's go back to Mr. I just matched something here. You see what it'll do is this guy right here says basically, oh, you got a hit. Well, mail the packet over here with the opaque set a particular way. Yep.
You don't even have to move. So the actual the actual passing of it to the next node is done in this branch down here afterwards, right?
Yeah,
So
again, it's a typical, you set next 0 and then you enqueue the packet where it's going. Now, this guy is the okay, you're going to take a little bit of a performance hit, but now you're searching multiple tables. You didn't hit in the first level, and it's going to sit there, run around, and it'll try to go. It'll say, okay, get a table. In other words, if at a it's basically a chained exact match scheme. That if you want to do more complicated things, you may need to do sort of multiple layers of tables versus here's well, let me see if I can sketch a case that a real world case that I've used. The first table you hit is matching. What's a good mobility sessions, and if you have an existing session, you know pretty well what you want to do with it based on a hit in the first table. The second table is a bunch of default rules that is a bunch of defaults that say, okay, what protocol is it? Who really wants to get this? And it'll actually direct the packets into a tunnel to go to a control plane agent to scratch its head to eventually program the first level table again. That's a fairly typical paradigm for using it.
So basically, the next step where the packet is going is either another table or is a node in the graph.
Well, the next step is always another node in the graph, one way or the other. And you notice this while one loop is going down a list of possibilities. I tell people, look, the first table, this is optimized for hits in the first table. Hits below there certainly work, but you're going to you're not going to be able to prefetch nearly as effectively at that point in the game. So, you do that, yada, yada, yada. And at the end of the day, if you really miss, if the last table is programmed, here we go. T0 is the current table's miss index. Okay, if you've actually totally missed, that's the action. Quite often that action is dropped.
Okay. Maybe another question that might be a lower level, maybe we need to take it
Yeah,
offline.
go for it.
How do you go from the performance point of view when you start with your initial vector of packets and some packets go left, some packets will go right, so you end up with splitting this vector into multiple vectors? How do you handle this case?
Okay, the typical game here is, imagine a world where you have, sessions, mobility sessions or something, and you assume that almost all of the traffic is going to hit. Well, the next index for all of those sessions is going to be, hey, I just hit on this. So the vector size really don't change much at that point in the game. Misses get directed to the control plane. But again, it has the same locality property. If you're mostly hitting on known entries anywhere in the table hierarchy, all of them are going to go to the same next node. They'll have different opaque data saying, oh, it's really this session or that session. Here's this credit card, go charge them some more, or whatever it is that you're doing based on classification. But the trajectory through the graph isn't going to get massively screwed up. In other words, you don't have an infinite fan-out. You could program it that way, but GAC, I've never even thought of wanting to do that. But typically, even though the table entries are different, the trajectory through the graph remains fairly constant in a situation where you're hitting on multiple sessions, different sessions, but almost all of the packets are hits. Well, depending on the use case you've programmed, almost all of those packets go the same, go out the same arc, so the vector size doesn't really change. Okay, go for it.
So on each node, then what you're saying is there is one hit entry. That's it. That is optimized. So you can't have multiple hit entries.
No. In each set of tables, the case that's optimized for is you can have 2-3 million matches. It's optimized for you actually hit in the first table you're searching rather than hitting three levels down.
So, okay, so table
in other
versus
words,
entry. So
slow down. Let me just show you the code because code uber alles here. This classify find entry guy assumes and requires that the hash bucket and the and the correct backing page have already been prefetched. In other words, the top of the the top of the classifier will compute the packet hashes and prefetch buckets and prefetch backing store pages. It then rumbles along. Notice this guy, VNet classify find entry, takes different arguments than the rather more general thing that you find in the while one loop, which is well, how would you put it? I mean, here what you're doing is you're not prefetching the bucket at all. You're doing go compute the hash and go see if you can find an entry. That happens from the second through nth table in the vertical set. So it's optimized to hit in the first, in the first set of sessions it's searching. Make sense? It's really a case of you're going to, unfortunately, you have to stare at the code a little bit to quite get it.
Sorry, can we just make this the last question and then let Dave finish because we're a bit over for lunch. I want to be sensitive. No, I want, and I also want to make sure you get a chance to finish. So if we could just make this the last question on classifier, and if you have any further questions, by all means, email them to Erin, and we'll make sure they get answered. Just want to make sure Dave gets a chance to finish, and we get you guys to lunch.
Okay.
So I get that it's optimized for the first hit. What's the performance impact of a miss and not making the first hit? What actually happens, and how?
Well,
I mean, I know it only happens occasionally.
Well,
but I'm
it's
just
not.
curious.
It's a perfectly valid question. If you close your eyes and think about unprefetched load stores, it a little bit depends on how big the tables are. The second table is probably going to be some form of misrule, of which you might have a very small number. In other words, you probably have the same mask as the previous table, and 3 or 4. If it's if it's IP4, IP6, MPLS, you might have a very small number of guys. Well, okay, you're going to take a couple of unprefetched misses. You have to integrate over the frequency, and it's not real obvious. So long as you're not missing constantly in the first table. And again, Could you imagine doing Bloom filters? Could you imagine doing a more sophisticated thing so you're not doing, you're not doing a long linear list? You wouldn't program, a whole bunch of different access control lists as, first we try this, then we try that, then we try the other thing. You'd try to program as, as few flavors as possible, but with as many matches as you like. In other words, as few different tables as you can, but the number of sessions is irrelevant, effectively. If you fall out of the first table, the code doesn't prefetch as effectively. Okay, everybody. Well, now I'm about played. Again, this is a study, send questions kind of problem a little bit.
Yeah, and like you can tell why I was excited about the classifier, right? There's a lot to it. There's some really cool stuff. And, so tomorrow morning, we've got 3 guaranteed sessions. FIB Walk-thru.
Yeah.
Absolutely, Pierre is going to go through his map case. Marcek is going to go through CSET. We'd love to have Florin be able to present. If there's extra time, perhaps we could revisit classifier, and note to Jerome for the European one, more time for classifier. And Damian had a really good point. We need to get some examples up on the wiki that describe more complex use cases and deeper in a tree. I'm happy to work with you on that. I know we were thinking about doing a little rewrite.
Yeah.
We'll see how it goes.
Yeah.
Pre or
Okay.
post that. But thanks.